And then finally, anterior to the ciliary body, a pigmented layer called the iris. So, the vascular layer is made up of the choroid, ciliary body, and the iris. Now, one of the purposes of the ciliary body is to hold the lens in place. So let's draw the lens in. Here's the lens. And the way it's tethered in place is through suspensory ligaments that attach both to the lens and to these ciliary processes like this. So they hold the lens in place. Now the ciliary bodies are going to contain smooth muscle. And what do we call this smooth muscle here inside? Ciliary muscles, which are innervated by cranial nerve 3, the oculomotor nerve. Okay.
And those help with focusing the lens? Is that
Yeah,
right?
yeah. As the ciliary muscle contracts or relaxes, it puts more stretch or less stretch on the suspensory ligaments. These suspensory ligaments will then pull on the lens. If they pull on the lens, they make it thinner. If these suspensory ligaments relax, the lens becomes thicker. Okay? And then this opening in the center of the iris is called what?
Pupil.
The pupil. It lets light through to the lens. Now, finally, the innermost layer is called the sensory tunic. And it's made up mostly of the retina. There's a line key for this, like this. And what we'll learn is that part of the retina will cover the ciliary body like this, as well as the posterior aspect of the iris. The part that covers the ciliary body and the posterior aspect of the iris, that does not have any photoreceptive cells, like cones or rods. Okay? But the neural part of the retina contains photoreceptors, cones and rods, that allow for vision. So this is the basic makeup. You have 3 different tunics. You got a fibrous tunic, a vascular tunic, and then a sensory tunic. Let's go to our PowerPoint now. All right, so to repeat, the fibrous tunic is made up of the sclera and the cornea. The sclera is the white of the eye. It's tough, it's continuous with the dura mater. It serves as the site of attachment for extrinsic eye muscles. The cornea is the window of the eye. It helps with focusing of incoming light rays. Remember that when light rays enter the eye, those light rays have to be bent and focused upon the retina. So that focusing activity, that refraction, begins within the cornea. Okay? As light rays move from the air through the cornea, they undergo some degree of refraction. He said it's avascular but contains numerous nerve endings. All right, this is the fibrous tunic here. This is the sclera, and it's continuous with the dura mater here over the optic nerve. Now, at this point, at which the sclera gives rise to the cornea, we refer to this region here and here as the limbus. L-I-M-B-U-S. The limbus is the site where the sclera then joins the cornea. Okay. We said the vascular tunic has 3 components. Another name for the vascular tunic, by the way, is the uvea. The largest component is the choroid. We said it carries lots of blood vessels. It's a dark brown pigmented layer that serves to absorb excess light. It also carries blood vessels with oxygen and nutrients to the other tissues of the eye. Anteriorly, it gives rise to these ciliary bodies, okay, that encircle the lens. Remember, it contains ciliary muscles that control the shape of the lens. And those extensions, those finger-like extensions, are called ciliary processes. Okay? And they're attached to those suspensory ligaments that on the other end attach to the lens. The iris is the colored part of the eye. Embedded within the iris, you have both circular and radial smooth muscle. We talked about that already. They allow for pupillary constriction, meiosis, and dilatation, mydriasis. All right, so in this case, this is the fibrous tunic. This second layer here is the choroid, which is part of the vascular tunic. You can see it has lots of blood vessels. Deep to this would be the retina, or the sensory tunic. Notice that when the choroid moves anteriorly, it forms the ciliary body, which is attached to the lens via suspensory ligaments, and then anterior to that, you have the iris. By the way, this ora serrata, okay, the serrated junction between the ciliary body and the retina. And you'll be able to see this on the sheep eye. Here, we see within the ciliary bodies the ciliary muscles. Okay? In this bottom image here, the ciliary muscles are relaxed, and you can see they stretch on the suspensory ligaments. They're taut. So these suspensory ligaments are pulling on the lens, keeping it thin. If the ciliary muscles contract, then actually it loosens, it relaxes the suspensory ligaments, which then allows the lens to thicken. Okay, that serves the purpose of accommodation for near vision. We've talked about this. Here's the iris. The inner layer of smooth muscle is circular smooth muscle, innervated by the oculomotor nerve. The outer layer is radial smooth muscle, innervated by sympathetics. Okay. So, parasympathetic innervation of the circular smooth muscle causes pupillary constriction. This occurs in bright light. In dim light, what happens? The radial smooth muscle contracts, providing for pupillary dilatation. Okay, and then the deepest layer is the sensory tunic. It's also called the retina, and the retina is composed of two different layers. The outer layer, which abuts the choroid, is composed of a single layer of cells, pigmented cells that abut the choroid layer. Okay? It's this pigmented layer that then covers the ciliary body as well as the posterior face of the iris. The inner layer is the neural layer. Okay? That doesn't come up over the ciliary body or the iris. Okay? That stays posterior to that ora serrata. The inner neural layer has three types of cells: photoreceptors, rods and cones; bipolar cells, or neurons; and ganglionic cells. Remember, we said that bipolar neurons are reserved for special sensations. Those special sensations are olfaction, vision, and hearing. That's where you find bipolar neurons. So you find them here in the neural layer of the retina. Okay. This shows you here, this yellow layer is the retina. It's deep to the choroid. Now, we see here the optic nerve entering the eye. Lateral to it is an area called the macula lutea. The macula lutea is the location along the retina where we tend to focus incoming light rays. It has a relatively high percentage of cones. Cones are the type of photoreceptors that are responsible for vision in bright light. They're responsible for high acuity vision, sharp vision. And so when we focus on an object in the distance, we tend to focus it on that object so that the incoming light rays strike the macula lutea. Now, in the center of the macula lutea is a region that contains almost 100% cones. That region is called the fovea centralis. What's the name of that condition where these cells begin to degenerate? It occurs a lot with old age. Macular degeneration. Macular degeneration. That's how older people lose their eyesight. Okay? And in the beginning, it affects mostly their central field of view. They can still maintain some peripheral vision because it tends to affect the cells in the macula. This is a closer view here of the retina. This is the pigmented layer, this single-celled layer that abuts the choroid right here. And then superimposed upon it here is the nervous layer, the neural layer of the retina. These are your rods and cones. These are cones, these are rods.
I'm sorry, can you point one more time?
These are the cones here, these are the rods. And these are the photoreceptors that respond to light rays, that trigger an impulse, an action potential in response to the reception of light rays.
Can you tell the difference because the rods are a little bit more elongated?
Well, if you look at the cones, they have a sharp, they have a cone-like end here, where the rods are straight.
The rods work out more.
Okay? So when action potentials, nerve impulses are triggered within these photoreceptors, they pass then into these bipolar cells, and from there into these ganglionic cells, the axons of which form the optic nerve. Notice that where the optic nerve enters into the retina, you see the head of the optic nerve. This is called the optic disc. All right, let's talk about those photoreceptors. Rods can operate in very low levels of light. Okay? They're more sensitive to light than cones. So they can operate in very dim light, but don't provide sharp images. Okay? Also, they don't provide color vision. You see gradations of gray. It's black and white vision.
It's like a shadow.
Right. Whereas cones operate in bright light, and they can provide high acuity color vision. So, for instance, in bright light, you and I are seeing all kinds of colors. If we turn the light down, we start to lose color vision. Okay? Colors become less vivid. All of a sudden, we start to see things in black and white. Yes?
You probably don't know this, but do dogs only have rods in their eyes then?
I don't know. I don't know about dogs.
Because they don't see colors.
No, I didn't know that.
They see shades.
Oh.
Like gray and black.
Well, maybe they just have rods then.
Maybe there's just one like that.
Now, the neural retina, remember that's the part with the photoreceptors, the bipolar cells, the ganglionic cells. That receives its blood flows from two sources. The outer third with the photoreceptors is supplied by the choroid vessel. So let's go back. Okay. So this layer right here gets its blood flow from the choroid. Whereas the deeper layers here, composed of the bipolar cells and the ganglionic cells, they receive their blood flow from retinal vessels. Let's go back. Here we see the retinal artery and vein that enter the eye through the nerve. And once they reach the retina, they branch and spread over the surface of the retina like this. Well, the central retinal artery provides blood flow to the deepest layers of the retina, composed of the ganglionic cells and bipolar cells, but the photoreceptors get their blood flow from the choroid. How does that make a difference? Well, if you have a retinal detachment, oftentimes that can occur with trauma, then what happens is the retina detaches from the choroid, and these photoreceptors lose their source of blood flow with oxygen and nutrients. So if that isn't corrected, what can happen? The retina can become ischemic, and over time you can lose vision.
How long would that take, though? I feel like that would be like almost instantaneous if your rods and cones were like...
Not instantaneously, but certainly if you don't get, it's considered an emergency. So it's one of those things like testicular torsion where you have a matter of hours to try to correct. And if you don't, then you start to lose vision. Now, the lens is biconvex. That means it bows out on both the anterior and the posterior face. As it thickens, it refracts to a greater degree. It bends light more. You may have heard of the term cataract. That's a clouding of the lens so that it interferes with vision. It's like looking through a frosted glass pane. Senile cataracts occur in the elderly, but there are certain groups that are at higher risk for early onset cataracts, like diabetics. Sometimes if you have trauma to the eye, you can develop a traumatic cataract. Okay, let's talk about the different chambers within the eye. We can subdivide the eye into an anterior segment and a posterior segment. The anterior segment is the part of the eye anterior to the lens and suspensory ligaments. Okay, so in my little drawing, even with the screen down, you can see the anterior segment. It's everything in front of this. Everything in front of the suspensory ligaments and the lens is part of the anterior chamber. Everything behind or posterior to the lens and suspensory ligaments are part of the posterior segment. Now, the anterior segment contains a free-flowing fluid called the aqueous humor. In many ways, it's very aqueous. It resembles water, but it contains solutes, just like the plasma does. Okay? We can take that anterior segment containing aqueous humor and further subdivide it into an anterior chamber located between the iris and the cornea, and a posterior chamber located between the iris and the lens. Okay? Now, the posterior segment, posterior to the suspensory ligaments and the lens, contains a different type of fluid called the vitreous humor. It's thick and it's gel-like. Okay? Whereas aqueous humor is produced every day and reabsorbed, the vitreous humor is produced during embryonic life. Okay? And once you produce it, you stop. So it doesn't continue to be produced throughout life. It doesn't get reabsorbed. Here we see that the ciliary processes, ciliary body, is what's responsible for producing the aqueous humor. And it travels from the posterior chamber through the pupil into the anterior chamber and strains